Hey everybody, this is Rebecca, and yep, we've had a cancellation due to those high winds and rains. And I have to say, I lectured this morning, and part of it was in the dark. So yeah, it's kind of a shame that we lost class. But I don't want us to get off track because I still want to maintain our schedule with giving you the exam on Tuesday. So I'm recording the lecture and putting it on Brightspace in hopes that you can take a few minutes to listen to it if you need the help. So here is the sections. Here are the sections that I wanted to cover in today's lecture. So let's go ahead and get started with this. All right, so let's take a bit to review what we've talked about so far. So in class, we took a look at these two arrows, and they tell us different things. The two-headed arrow tells us that we're dealing with a reaction that can go forward as well as in reverse. And when we have that scenario, we're going to have a reaction that's going to undergo the establishment of an equilibrium, as opposed to the single-headed arrow, which is basically a reaction that moves forward to completion. The difference between these two equations is that when we have a reaction that can establish equilibrium, we're always going to have some reactant in addition to product in our container. Whereas if we have a reaction that moves to completion, we'll have nothing left but product at the end of the reaction. So that's a little bit about that. Now, what about this whole idea of dynamic equilibrium? Well, what is dynamic equilibrium? Dynamic equilibrium is when you have the rate of products forming equaling the rate of reactants reforming. So our double-headed arrow tells us not that we have reached this point where we have an equal amount or an established amount of reactants to, to products, but that the rate of reactants turning to products and products returning to reactants is now equal, and so that when we take a sample in our vat, we'll see a stable amount of product and reactant. That's what dynamic equilibrium is really all about. Then we talked about the law of mass action, and what is that telling us? Well, it's saying that there's a relationship between the chemical equation and the concentrations of the reactants and the products. So we have our chemical equation that looks like this, and we can actually figure out the equilibrium constant by putting those values, that is the concentration of our products and the concentration of our reactants, into this sort of equation and figure out what that equilibrium constant is. And then we learned some rules about the governance of the relationship between our equilibrium constant and the chemical equation. One of those rules was this, that when your equilibrium constant goes in reverse, it's going to be equal to the inverse value of your equilibrium constant going forward. And we brought up a couple of equations that looked like this. So if our equilibrium constant goes forward, we're going to end up putting our products on top, our reactants on the bottom, and if we're running that equation in reverse, then our reactants go on top and our products go on the bottom. Another rule that helps with the governance of the relationship between the equilibrium constant and the equation is this right here. And basically what this is saying is that if you were to take your chemical equation and have to multiply it by a value such as N, it's going to change your equilibrium constant to that power, whatever the power of N is. And it would end up looking something like this. And then the third law that tells us about the relationship or the governance of the relationship between the equilibrium constant and the chemical equation says that if you're trying to add a couple of equations together, you can do that, and you would be taking those concentrations, and if you had any repeating values top and bottom, you would cancel those out, and you would in essence be creating a new equilibrium constant. So these were the concepts that we went over in class the last time we met. So let's now talk about some new material. So far when we've talked about these equilibrium constants, we've been talking about chemical equations that are dealing with products and reactants that are gases. And given that we know what that relationship is, that chemical equation is, we are able to come up with an equilibrium constant. Now, the values that we're using in order to calculate the equilibrium constant are going to be the concentration of our products and the concentration of the reactants. So we're going to be measuring these in moles per volume. So we're counting the particles of gas in a given volume of that gas. And if we're talking about more than one gas interacting, then we're talking about a mixture. And then if we're talking about mixtures, we can start to maybe ask, is there a way that we could use the pressure of those gases to come up with an equilibrium constant based upon the pressures? And the answer to that is yes, we can. We can use the partial pressures of gases in a gas mixture to come up with an equilibrium constant, as long as we know what those pressures are. So let's see how that works. So let's bring up the ideal gas law. Now, if we look at the ideal gas law, this is pressure times volume is equal to the moles of the gas that we're talking about times the gas constant and the temperature at which this scenario is taking place. Now, if we think back to what our equilibrium constant is based on, it's based upon the concentration of either a product or a reactant. Let's say that A is a reactant in this case. And a concentration is given in terms of mole per volume. And what do we have in the universal ideal gas law but a volume and a mole? So that we are capable of saying that our concentration of our reactant A is equal to the moles of A over the volume that that gas is occupying. Well, if we apply the same overlay to the ideal gas law, we can say that the partial pressure of our reactant A is equal to the moles of A over the volume that is being occupied by the gas times the gas constant and the temperature at which this is occurring. And if we isolate the moles per volume, it's going to be equal to the partial pressure of A over the gas constant times temperature. And in essence, we have found a way to correlate the concentration of reactant A to its partial pressure, provided that we can also have some idea of what the moles and the volume are. Now, through a great deal of substitution, we can take our equation and we can take the rule for our equilibrium constant and make the substitutions that we just calculated, and it would end up looking something like this, where we would have the partial pressure of our product C and the partial pressure of our product D over the partial pressure of our reactant A and the partial pressure times the partial pressure of our reactant B. So we made the substitutions based upon using the universal gas law. And if we do some more mathematic gymnastics, we can kind of pare this down and basically say that, yeah, we can come up with an equilibrium constant based upon the partial pressures, and it's going to be equal to the equilibrium constant of our gases times the gas constant times the temperature at which all this is occurring, given the change of raised to the power of the change of moles that is in our equation. Sounds crazy, but it all works. So here's what we've come up with as far as coming up with a equilibrium constant using partial pressures. So we might want to ask ourselves, what if there is no change in the number of moles in over the course of our equation? And where am I getting the moles from? Well, you have to think back to stoichiometry. It would be the little a and the little b, and then the little c and the little d. So the little a and the little b representing the coefficients of our reactants, and little c, little d being the coefficients of our products. Now, what if there is no change, like the difference in the coefficients, the summation of the coefficients of our reactants is equal to the summation of the coefficients of our products? Well, then what that means is that our equilibrium constant given the partial pressure of our gases is going to equal the equilibrium constant based upon the concentration of our gases. So that zero exponent actually only gets applied to the R and the T, I guess is the way you could think about that. So that's a little bit about that. Now what about the units? Well, because these are constants, we don't typically think about them in terms of units, although you could kind of say that if you were using the concentration of A and which is going to be in molarities, that is mole over volume, then your equilibrium constant would be in molarity as well. And if you were using the partial pressure and those units were in atmospheres, then your equilibrium constant for your partial pressure would also be in atmospheres. I mention this because it's in the book, and later on it might be helpful if we're trying to do a calculation to have an understanding of what sort of units that we're dealing with. So far in our conversation, we have been talking about finding the equilibrium of gases, and we were given an equation that dealt with nothing but gases. But what if not all the compounds that we're dealing with are gases? What if we end up with something that has a solid in it, an equation that has a solid or a liquid or even an aqueous solution? How do we handle those sorts of things? Well, like I said, when we've been dealing with gases, we've been dealing with concentrations, and a concentration of gas is measured in moles per volume. So your concentration could be different based upon the number of moles that you have, or it could be different based upon the volume of your container, because remember, a gas will expand to occupy the entirety of a container. Now, if you're dealing with something like a solid is going to be measured in density, which is a mass per volume. And mass per volume doesn't change. It is always going to be the same, whether it's occupying, whether you have a lot of it or whether you have a small amount of it. A solid doesn't change to occupy the space that it's put in. It is what it is. And the same thing is true when you're dealing with something that is a pure liquid, something that is just a pure fluid substance. The same thing is true with that. It has a specific density. Like water. Water has a density. You're going to have so much mass given a particular volume of water, and it's not going to change. Now, if you were to add salt to that water, you could end up creating a little bit of a variance there, and you could have, you would be talking about a concentration of salt in the water, and then that would be a whole different thing. But if all you're talking about is water, then you're talking about the number of, or the mass of water given a particular volume, and like a solid, your liquid does not expand to occupy the entirety of the container that it's in. So when you have this scenario, where if you were to have an equation where one of your compounds, whether it's a reactant or a product, was a solid or a pure liquid, you would not include those in your equilibrium constant calculation. So let's take a look at what that would end up being. So here we have an equation where we have reactants A and B, both of them are gases, and then we have a product C that's a gas, but then we have a product D that ends up being a solid. In order to come up with the equilibrium constant, our formula would end up having C in it. The only product would be C. We're not going to include D in this, but then we would have both of the reactants A and B because they are gases. This is what this looks like when one of your compounds in your equation is something other than a gas. So a moment ago I mentioned aqueous solutions. So what about those aqueous solutions? Well, how are they measured? Aqueous solutions are measured in mole per volume, just like a gas. So we would include those. So let's take this equation right here where we have carbon dioxide and water, and it's going to create hydrogen ions and some bicarbonate ions. And if we look, we have carbon dioxide gas, we have water, which is a pure liquid, and then we have hydrogen ions in our liquid and bicarbonate ions in our liquid. So what is our equilibrium constant formula going to end up looking like? Well, it's going to look like this, where we're going to take our our products of our hydrogen ions, the concentration of hydrogen ions and the concentration of bicarbonate ions, and we're going to put it over our carbon dioxide, and we're going to leave out our water because our water is a pure substance. That's what that looks like. So far, we've been talking about just setting up a formula for our equilibrium constant, and we haven't even plugged any values in. So I guess the question is, if we're given concentration values of our products and our reactants, can we actually calculate a value of our equilibrium constant? And the answer is yeah, we can. It's basic math. We can do that. So how is this going to look? Well, it's going to involve something called an ICE table. An ICE table is going to help us find our values at equilibrium. So what does ICE stand for? Well, the I in ICE stands for the initial concentration of all of our players, the products and the reactants. The C stands for the change of amount that everybody goes through as a result of this reaction. And the E stands for the equilibrium concentrations at the end of the reaction. And we'll take these end equilibrium amounts, and those are going to be the values that we use in our equilibrium constant formula to actually get a value of our K of C. And these values are going to be in moles per liter, so it's a mole per volume value. So let's take a look at this. Okay, so let's bring up an equation. So here we have carbon monoxide and hydrogen, and we're going to create some methanol. And this is an equilibrium reaction, and we know that because of our two-headed arrow. And we're given some concentrations in our problem. I want to say this is example 15.5, so you could follow along in your book if you wanted to. So we're given an initial amount of carbon monoxide of 0.500 moles per volume, and we're given an initial hydrogen gas concentration of 1 mole, or 1 molarity, and then we're also giving a concentration of carbon monoxide at equilibrium, and we're being asked to come up with the value of our equilibrium constant. So with this information, we can actually do this, and I'm going to show you how that works. So if we bring up an ICE table, it looks like this. So you see down the far left, I have the letters ICE, and in that row for I, we're going to put our initial values of our products and our reactants, and then the amount by which everybody changes, and then we're going to do some basic math, which is we're going to subtract the change. Well, it depends on what we're doing. If we're talking about reactants, we're going to subtract the change from the initial and calculate the equivalent, the equilibrium values, concentrations. And if we're talking about the products, then we're going to actually add that change. So let's actually do all of that. So the first thing we need to do is label our columns with each of our players. So here we have one of our reactants, carbon monoxide, and then here's our hydrogen gas, and then in our last one we're going to have our methanol. Now you notice that I put a big heavy line between the reactants and the products, and that kind of helps me visually make sure I'm doing all the math right. Before I get too much further along, the other thing I want to make note of is the ratio that all of these occur in this reaction. So we have 1 carbon monoxide for every 2 hydrogen gases and 1 methanol. So the ratio is 1 to 2 to 1, and that's going to become important to us a little bit later on when we're doing these calculations. Now we're given the initial amount of carbon monoxide, and that comes in at 0.5. And then we're also given an initial amount of hydrogen gas, and that comes in at 1.0. And then we're given an amount of carbon monoxide at equilibrium at 0.15. Now these values are given. There's one more value that we can make an assumption about, and that is the amount of methanol that we have at the beginning of our reaction. So at the beginning of our reaction, how much methanol do you think we have? Well, we have none, because at the beginning of our reaction, we haven't formed any products yet. So in this little maneuver, we're able to plug in all of our initial values because of what we were given and the assumption that we can make that we start off with no methanol. Now, from this point, we're going to have to do a little backward thinking, and we're going to start by looking at our carbon monoxide. So if we're given an initial amount of carbon monoxide and a final amount of carbon monoxide, are we capable of figuring out how much change our carbon monoxide underwent? Sure we can. And if we just subtract the 0.15 from our 0.5, we come up with 0.35. So our carbon monoxide lost 0.35 moles of gas in this reaction, and that's how it went from 0.5 to 0.15. Now, this means that everybody underwent this sort of a change. If you are a reactant, you underwent a loss in this amount given the appropriate proportion. And I'll tell you what I mean by that in a minute. If you are a product, you gained by the appropriate proportion. So what I mean by losing by the appropriate proportion is that we wouldn't simply plug in a negative 0.35 for hydrogen, because the ratio of carbon monoxide to hydrogen is a 1 to 2. So we have to take that into account when we're figuring out the mole loss or the molarity loss, and we have to bring that 2 down and multiply that value by 2 for our hydrogen. Now, what's that value going to be for our methanol? Well, we're not going to lose, because what we're losing on the left side of the transformation arrow is going to actually be experienced as a gain on the right side of the transformation arrow. And that is how we're going about creating our methanol. Now, at this point, we can do some basic adding and subtracting, and we can come up with our equilibrium values for not only carbon monoxide, well, that was a given, but we can do the calculation and come up with the equilibrium value for our hydrogen gas as well as for our methanol. And these equilibrium concentrations are going to be really important to us, because these values are going to drop into this equation right here, and it will allow us to actually come up with a value of our equilibrium constant. So if we take the concentration of our methanol and we put that over the concentration of our carbon monoxide times the concentration of our hydrogen squared, we actually end up with a number, and it comes up to be 26. So this is how you use an ICE table and a few given values to figure out an actual value for your equilibrium constant. So far, we've been talking about these reactions occurring at the moment that equilibrium is established. But what if you had a reaction that you wanted to actually gauge what was happening over the course of the equilibrium being established? Is there a way to calculate that? And of course there is. That's why I'm bringing it up. And we would use something known as a reaction quotient. And a reaction quotient looks suspiciously like an equilibrium constant. It's the same values. But how is it different? Well, for one thing, you've got a Q in the beginning of this as opposed to a K. But what is the real significance here? Well, the K is specific to the moment of equilibrium, whereas the Q is specific at the moment that the reaction is trying to go into equilibrium. So we might be taking our Q at the moment that we drop in our reactants together and they start the process. And in that case, we would actually have a lot more reactants than products, and we would come up with one value. If we waited several minutes, we might be in the phase of this reaction where most of the reactants have moved into products and are now starting to reverse and go back into reactants. But in that moment, we actually have more product than we have reactant. And if this is the case, we can kind of figure out where we are in the progression of the establishment of our equilibrium, and that's the value of the reaction quotient. And that's why the number actually still looks, the equation still looks like the equilibrium constant, is because we're finding the equilibrium in a moment of time, as opposed to once all the dust is settled and everything that's going to form is already there and the reactions backwards and forwards have equalized. So let's say that we were at the very beginning of our reaction and all we had were reactants and we hadn't formed any products yet. Then our reaction quotient would be equal to 0. That means we haven't gotten anything. And what if we were at that moment in time, we were just so very lucky that in a moment in time, we took a sample of our product and we found out that we had in our container nothing but product, and we hadn't started to reform any reactant. Well, mathematically, that would say we'd gone to infinity. But the idea is that in a real reaction that has the possibility of establishing equilibrium, you're going to end up coming up with some sort of a number, because you're not going to take your sample at the moment that you drop your reactants in. And even if you did, you couldn't be quick enough to take that sample before anything formed. You'd always have something. Now, understanding the relationship of the reaction quotient to our equilibrium constant kind of tells us a little bit about where our reaction might be in the process of moving towards equilibrium. So, for example, if we were to have a reaction quotient that was less than our known equilibrium constant, then we could kind of speculate that the reaction was going to move back towards the creation of products. If we had a reaction quotient that was greater than our equilibrium constant, then we could predict that we were going to see the creation of more reactants as this reaction moved back to the other way. And if in this magic moment we were to take a sample of our product and find that our reaction quotient was actually equal to our equilibrium constant, then we could kind of anticipate that no further change would occur, and that in fact we had probably reached an equilibrium with our reaction. So basically no new math here, but just an understanding of what the reaction quotient is trying to tell us. And that is it for today's lecture. So I hope you find this helpful. And what I plan on doing when we get back on Tuesday, provided we don't have high winds or floods or any other catastrophe, we'll go over some of these homework problems and finish up this chapter, because it's just a little bit, just 2 little sections, and you'll get your take-home exam, and off we go. All right. Well, thanks for watching, everybody. I'll see you on Tuesday.